So we considered the effects of each layer on differential cryptanalysis. Namely, we have seen that key addition layer and the permutation layer does not affect differential cryptanalysis, but problem arises at the substitution layer. So in this video, we will talk about the differential cryptanalysis of present. We will see an example of an attack on present, not the full cipher, but the reduced version. And in order to do that, we have to see how the substitution layer affects differential cryptanalysis. In the case of present, we have S boxes, and actually a single S box is used 16 times in parallel. So we have to consider how this S box affects when we produce an input difference. So let's look at the S box. Recall that this is presence S box. We can have 16 different input, and we can have 16 different outputs. So this is like a permutation. It is a one-to-one and onto map. So it is a bijective S box. And this doesn't have to be always this way, but for the present cipher, we need a bijective S box. So consider every possible XY input pairs with X XOR Y equals to I, and count the output differences where SX XOR SY equals to J, and construct the table with this count as the ijth entry. So this means that fix I, for instance, if you start with 0, this means that when this is 0, X equals to Y. So consider every possible input pairs. In this case, since Y equals to X, we will have X pairs. So we will have to check what is the XOR of SX XOR SX, which is again 0, since X equals to Y. So this means that for the possible 16 inputs, and these inputs are 0, 0, 1, 1, 2, 2, 3, 3, and so on, we always see the output of 0. So in such a table, we will see that if the input ijth entry, so 0, 0th entry, is 16, but 0, 1 or 0, 7th entry is 0, because you cannot give the same input difference and observe a different output difference, because when X equals to Y, this Sx would be equal to Sy. So this should be 0. But now consider, so this would be your first 0th row. So consider the first row of your table. So in this case, you say that I equals to 1. So this means that X XOR Y equals to 1. So if you take X equals to 0, Y has to be 1. But if you take X equals to 1, Y have to be 0. If you take X equals to 2, Y equals to 3. If X equals to 3, Y equals to 2, and so on and so forth. So if you perform this operation, you can see that we are actually dealing with even values here, because in this example I'm just mentioning, look at S0 XOR S1, it will be something, but then look at S1 XOR S0. It is the same thing, because we are just changing the places of X and Y. Since X and Y can always swap, whatever J value is observed, it has to be even at the end. Long story short, let's construct the table like this. So all you need to do is write a simple programming code. Actually, 2 for loops inside each other will do this trick. So it will be like 5 or 10 lines of code. But for this S box, this should be the table you need to get. So for the input difference 0, which means X equals to Y, you will always observe Sx equals to Sy. So this is why you have 16. As you can see, this is 2 to the 4. And since this is an S box of dimension 4 times 4, this is why we have 2 to the 4. So if you construct this table for AES, the S box is now 8 times 8. So this value should be 256. But of course, the table would be a lot bigger, because you can have 256 different input differences. So for the input difference of 1, it is calculated as follows. 4 times we see the output of 3. 4 times we see the output of 7, and 4 times we see the output of 9, and 4 times we see the output of D. as you can see, if you sum these values, it has to sum up to 16, because since you are giving 16 different input pairs, you have to observe 16 different output. So the summation of each row and each column actually should sum up to 16. And again, every value in the table has to be even, because a pair of xy and yx would always give you the same result. So this is the table. So this actually gives a statistical approach now, because in our previous video we talked about that we don't know the inputs of this S box, but we know the input difference of this S box. So one input to this S box, let's say I, and the other one is I prime. We don't know what they are, but we know the XOR of these values. So if you know the XOR of these values, let's say that it is 2, by looking at this table, we can see that the output difference can be 3, 5, 6, A, C, D, and E. But more importantly, as you can see, some values are 2, but there is a value of 4 here. So probability of observing 5 is larger than the other values independently. So this means that 4 out of 16 times you have to see the output of 5, but 2 out of 16 times you will see 6, 3, and so on. So as you can see, now we have something in terms of probability, and now we can talk about high probability, because the largest value in this table actually gives a direction for the cryptanalyst. So we can use that value and make some assumptions. So this table actually can help you to create differential characteristics. So, and by the way, I probably told before, but let's remind, this table is called a difference distribution table, which is shortened as DDT. So the highest value is in the DTT, of course, except the first entry here, because it is always 2 to the n, where n is the dimension of the S box. So if you don't consider this value, just consider the remaining part of the table and look at the highest value in that table. In this example, for the present, the highest value is 4. So that value is called differential uniformity. So higher is better for the attacker, because this way they can find a property that is going to happen with high probability. But for the designer, lower is better. So since we already know that all of the values has to be even, so the best S-box and the best DDT table we can hope for this dimension is a table that is full of zeros and twos and not fours. So it will be wonderful if we have only zeros and twos and no fours. But in this case we have, but it is not because present designers chose a bad S-box. It is because for this dimension, you cannot have such an S-box. Unfortunately, we cannot have that security. We cannot have anything better than 4. So for the dimension of 4 times 4, the lowest differential uniformity you can get is 4. This is why present designers chose such an S-box. So high differential uniformity provides characteristics with high probability, hence lower is better for the designer and for all of us. Values in DDT is even because the pairs xy and yx provide the same difference, because sx XOR sy would be equal to sy XOR sx. So this is why every value appears twice. Thus, the theoretically best achievable differential uniformity is 2 for every bijective S-box actually. But this theoretically best achievable uniformity, as I told you before, is not possible for 4x4 S-boxes. But we know some mathematical constructions to obtain this for odd dimensional S-boxes, like 5x5. But we don't have such a technique for even dimensional S-boxes. So since we couldn't find and by computationally, we can check every 4x4 S box. Actually, not all of them, but by using some equivalency, we can actually traverse all of the possible 4x4 S boxes and observe that there isn't any with a differential uniformity 2. So since we couldn't get it for 4x4 S box, people for a long time thought that it is not possible to have this for even dimensional S boxes. And S box of AES also has differential uniformity 4. So there was a belief that we cannot have this. So this is just theoretically achievable. As I told you, for odd dimensions, we can construct such S boxes, n by n S boxes. And for n equals to 4, there is no such S box, which can be computationally checked. But strangely, in 2010, Dylan found an S box which has differential uniformity 2. So we call 2 uniform. 2 differential uniform actually is a better term. So for n equals to 6, we now know that it is possible. So the big problem is, can you find a 2 differentially uniform 8x8 S box? Because if you can, then that would be something better than the S box of AES. So this is still an open problem, and but the source space is really huge. Even with some techniques, we cannot traverse the whole space. So this is why we cannot computationally check if such an S box exists or not. But this is a huge open problem and a very interesting one. So let's see some design criteria of presence S box. It is differentially 4 uniform because this is the best that we can get. So designers chose it like that. And present has no fixed point. This means that you don't have any x which will give you x equals to sx. So if you go back to the table, as you can see, 0 doesn't go to 0 or 5 doesn't go to 5. So you cannot see any fixed points. There are some S boxes that have fixed points. So we have ciphers that use that kind of S boxes. But although directly it is not a weakness, keeping something the same might cause some problems. So this is why it is not preferred. Moreover, one of the design criteria is as follows. 1-bit input difference never provides a 1-bit output difference. So the input differences 1, 2, 4, or 8 never give you so x or y when it is equals to these values. The sx or sy will never be equal to these values. So actually you can check this from the DTT table too. So look at the 1. So your input difference is 1. Look at this row, and you will see zeros everywhere when the output difference is 1, 2, 4, and 8. Same for 2, 4, and 8. So it is chosen like this. So this is to actually cause a better diffusion, because a small difference would cause bigger effects, let's say. So how can we use this DDT table to create a differential characteristic? Here we take an example from Wang's differential attack on present. So in this paper, they provide a 4-round iterative characteristic of present. I will explain what it is, and I will also explain why it is called iterative. So the attacker says that if you choose an input difference as 4 for the S boxes 0 and 3, so if you go back to the picture, this means that here we have some input we don't know, and in a different encryption we also have another input here. Again, we don't know, but we know that their XOR is 4. Also, same is here, so there's some value here and something else there, but their XOR is also 4, and we don't have any difference in other places. So whatever this value is, it is also the same in the pair that we are encrypting. So there are 0 differences here. So question is, What will be the effect of such a difference when you have input difference 4 and 4 here? What will be the output difference? So the attacker says that let's consider the cases when the output difference after the S-box operation in round 1 is 5. So this means that your input difference is 4 and output difference is 5. So this is not always the case, but we have to go back to the DDT table and see how frequently it happens. Look at the row 4. As you can see, the value is 4 for the output difference 5. So this means that 4 out of 16 times this is the case. So we are only focusing on those cases since they don't happen with probability 1. This happens with probability 4 over 16, which is 1 over 4. Same is also here. You also give the same input difference to the different S-box, and you want to see the output difference 5. This also has a probability 1 over 4. If you multiply both probabilities, since these are independent events, the probability becomes 1 over 16, which can be written as 2 to the minus 4, which equals to 1 over 16. So this means that take a random input, then change the 2 bits that corresponds to these 2 places. Put them inside the S-boxes of present. You will observe the output differences 5 and 5, 1 out of 16 times. So this is as simple as that. This is what it tells. So this way, for the substitution layer, we can have a one-round differential characteristic like this. When you perform the permutation operation, these bits are moved to some other places. And from here, we observe that it goes to x0 and x8. So this means that after the permutation layer, after the permutation layer, this differences goes to here and also goes to S8. So after the next round, you have differences 1, 0, 0, 1 here and 1, 0, 0, 1 here. In hexadecimal notation, this is 9. So this is why this after the permutation layer, you have input differences 9 for the S-boxes 0 and 8. And this happens with probability 1 because, as we already mentioned, this permutation layer doesn't introduce anything probabilistic. It happens with probability 1. Now we look at DDT table again and check what is the probability of observing output difference 4 when the input difference is 9. As you can see from here, it is the same. So we are guessing that at DDT table, we will observe the value 4. But let's look at it again. For the input difference 9, we see that the output difference is 4 times. So the probability is the same. And so on and so forth. Let's look at here because the probability is different. Here, the attacker wants to see the output difference 1 and the input difference is 5. Of course, this happens twice. And there's a typo here. This should be x14, not 11. They should be the same, okay? Because this is the S-box layer. So let's look at what happens when the input difference is 5 and output difference is 1. Let's go back to the DDT table. When input difference is 5, output difference 1 is observed 2 out of 16 times. So this is probability 1 over 8. If you multiply it with itself, because we want to see it twice, 1 over 8 times 1 over 8 is 1 over 64, which is 2 to the minus 6. And after the permutation layer, we see the input differences 4 and 4. So this means that if you take a random input, 64-bit input for present, and encrypt it under an unknown secret key for 4 rounds, you will obtain some output. And now take the same input you used, but flip 2 bits that corresponds to these 2 places. Encrypt it again, and now you will have another output. XOR both outputs. We claim that you will see difference only at these 2 bits with the probability, which is the multiplication of all of these values. So if you multiply all of them, you will have 2 to the minus 18. So with probability 2 to the minus 18, this input difference will produce this output difference after 4 rounds of present encryption. As you can see, these places are the same with it. This is why we call it an iterative characteristic, because if you take this table and put it below it, now you obtain then 8 round characteristic, but of course the probability is now squared. So instead of 2 to the minus 18, it will be 2 to the minus 36. So another way to interpret this table is as follows. I told you that this input difference produces itself after 4 rounds of encryption under a secret key that you don't know, with probability 2 to the minus 18. This means that if you take, for instance, random 2 to the 30 input elements with this difference and encrypt those pairs and look at the output difference, since you use 2 to the 30 pairs, and this probability is 2 to the minus 18, you expect to see 2 to the 12 times this output difference, which is like 4096. So this is your expected value. So this is a property that doesn't happen for every cipher or a random permutation, but it happens for present. So you have a distinguisher for 4 round present. So if we assume that these probabilities are independent, then the 4 round characteristics holds with probability 2 to the minus 18. Input and output differences are the same, so we can put the same characteristic below to obtain 8 round characteristics with probability 2 to the minus 36. This is why we have the name iterative. So Wang in his paper constructs an even longer differential characteristic, and they show that the 14 round characteristic has probability 2 to the minus 62, and it is defined like this. So if you give the input difference 7 to these two S boxes and no differences into the other S boxes, you will observe the output differences in these two S boxes with probability 2 to the minus 62. Then, if we add 2 rounds to the bottom of this characteristic, the output difference should be in the form this, because if this difference is encrypted, you will follow the S-box layer and permutation layer 2 rounds, and you will realize that it would affect these nibbles, but not these ones. So this is why they are 0. With question mark, we represent the difference whose value we don't know. So if you actually write it here, you will realize that this input difference would produce some output difference, but for some reason you wouldn't see any difference in the least significant bits. Actually, we call this property as undisturbed bits in a different study. So this question mark actually affects these question marks, and this will be the output difference you would observe. So if you write them in hexadecimal notation, this is what you get. So this is how you perform the attack actually. So the attack procedure is explained in this slide. First, we start with the data collection part. Gather n plain text ciphertext pairs with input difference given like this, which is actually the one obtained by Wang. And the output difference should be in this form, which is we observed here. And since as an attacker, you can only get input and output values, not the intermediate values, this is a realistic scenario. You get the n plain text ciphertext pairs in this form. So this is a chosen plain text collection. Then we perform a key guess part. This is actually the cryptanalysis part. Partially decrypt these pairs with every possible key bits of rounds 16 and 15 that corresponds to the S boxes with non-zero difference. Correct key should have the highest counter. So this means that you have n pairs with this output difference. Now, perform an exhaustive search-like attack and perform a 2-round decryption with every possible key. And when you observe this difference, 9 and 9 here, for the key that you are performing the exhaustive search, increment this counter by 1. So initialize counters to zeros first for every possible key, then increment this value when you observe this value. So since we don't have to guess every round key bit because we don't need the values here. This exhaustive search is something manageable because it is not 2 to the 8 or 128, but it should be something less. It depends on how many S boxes times 4 that you need to guess the key. So you perform this attack and increment the counters. We assume that the highest counter will correspond to the correct key, because again, we mentioned this, the wrong keys should act like a random permutation. This is actually what the wrong key randomization hypothesis is. So this way you can capture some round key bits, and from those round key bits, you actually capture some master secret key bits. Now you don't know the remaining key bits. You can just perform the real exhaustive search on the remaining key bits to find the whole secret key. So there's one thing to say actually here. So in the paper, Wang says that this is the attack, and instead of a single characteristic, actually they are using 24 characteristics. That's somewhat similar to this. And they claim that they can capture 32 bits of the key with this many encryptions, and the remaining 48 bits, since present has 80-bit version. So you capture the 32 of them in the first phase of the attack, then you perform an exhaustive search for the remaining part, and so your attack complexity is actually 2 to the 48 16-round present encryptions. So this is not actually the case, because theory and practice does not match in reality. Most of the time, attacks cannot be verified in practice due to the high data and time or memory complexities. Actually, the previous attack doesn't have that much high complexity, so you can maybe practically check, but again, 2 to the 48 is not that easy for everybody. It will take maybe months for you. But reduced versions of the theoretical attacks should be experimentally verified to check if anything is overlooked. Wang's attack should be modified due to the existence of differential factors. This is a thing that we actually discovered a few years ago. We observed that when you perform this attack, Wang claims that you can capture 32 bits of this round keys, because you are guessing key bits here, 4 bits here, 4 bits here, and so on. But when you perform the attack, you will observe that not the correct key gets the highest counter, but some other keys also get the same counter with the correct key, and you cannot distinguish them because all of them gets the same counter. This is due to the existence of differential factors, and we define the differential factors in this form. So for an S box and for a fixed mu, if for every x and y, that is where you have Sx XOR Sy equals to mu, if you also have Sx XOR lambda XOR Sy XOR lambda equals to mu, then we say that the S box has a differential factor lambda for the output difference mu. Of course, if you take mu equals to 0, you will have every possible lambda that satisfies this equation. So we are looking actually non-zero mu's, so we call them non-trivial differential factors. So this means that mu remains invariant for lambda. This is important because when you're actually guessing the key, you are XORing the input value with the round key bits. This is actually corresponds to lambda. So this is why when a counter of a key is incremented, that key XOR lambda also incremented. So two different keys always get the same counter. This is due to the differential factors. So this is why we always insist that when you obtain something theoretically, try to verify the toy versions of the theoretical observation. In this case, instead of trying to perform the 16-round attack on present, you can reduce it to 6 rounds or maybe even shorter and perform the attack and try to capture the key. If somebody did that, they would observe that due to the differential factors, you cannot capture the keys directly. So with small modification, this attack actually works. So you have to be careful when you are performing the attack in practice.